Hi guys, right now I'm going to talk about the error limit for the trapezoidal and Simpson's rule. I already wrote some stuff in here. Okay, so let me just for now just forget all of these things, and let me just say that for the trapezoidal rule, because these are approximations, there's going to be an error. Okay, so the limit of the error for the trapezoidal, I'm going to say like error, and I'm going to put trapezoidal, and this is going to be an absolute value. The error is going to be less than or equal to k b minus a. Okay, if you make an integration from a to b of f of x dx, so it's going to be b minus k divided by 12 n squared. For the Simpson's rule, I'm going to put an s here. Okay, going to be less than or equal to k, and this thing here I'm also going to put an absolute value, k times b minus a to the fifth divided by 180 n to the fourth. Okay, so this is not the error, it's the limit of the error, it's the worst case scenario. The error is never going to be larger than this formulas. I'm not going to show where these formulas come from now. I'm going to do that in the following videos. This is cubed. Okay, so kb minus a cubed divided by 12n squared, and this is going to be kb minus a to the fifth divided by 180 n to the fourth. K over here is equal to the maximum value of the second derivative of f of x going from a to b. Okay, k in this case here in the Simpson's rule is the maximum, and it's the maximum absolute value, right? It's going to be the maximum absolute value of the fourth derivative of f of x going from a to b. So let's just say that you have you got an interval here, another one here, another one here, another one here, another. Okay, let's just say that you got a 3, in here you have a minus 15, in here you have a 40, and in here you have a minus 60. You're going to pick this one up, okay? It's the maximum, it's not the maximum value, it's the maximum absolute value. So this is the maximum value, absolute value. This is going to be 3, this one's going to be 15, 40, and 60. So you're going to use k equals to 60, right? For all intervals. Actually, that's why this is the limit of the error. The error in practicality, in reality, is going to be a lot less than this. But this is going to be the limit, okay, of the error. The error is never going to go beyond this. Where these formulas come from, I'm not going to show now, because I'm going to make special videos for this formula and another special video for this one. And these videos are actually content that I'm copying from somebody else. I didn't develop these proofs, but I'm not going to show them now because they require integration by parts. And you have to know something of Taylor polynomials and Lagrange polynomial to derive Simpson's rule. So that's why I'm not going to show these things now. All right, I'm just going to apply one of these formulas, this one right here, to an exercise that we're going to do now, to show how this is one of the ways that you can use this in reality. All right. So I already wrote some stuff in here. So you have an integral from 0 to 1, 1 plus x squared. And let's just say that you are integrating with this within this domain only, and you want to make an error that is less, okay, the total error, you want to approximate this with the trapezoid rule. You're not going to actually integrate this. And the total error has to be less than 0.01. So whatever the result is, it has to be less than or equal the result plus 0.01 and greater than the result minus 0.01. Okay, so the result is going to be within this range here. That's the idea. So you have to find what is k again. This is the formula, and I said that k is the second derivative, right? It's the maximum absolute value of the second derivative from a to b, which is going to be from 0 to 1. The first derivative I've already calculated here is x divided by the square root of 1 plus x squared. So all you got to do is to use the sum rule, right? I mean the product rule for differentiation, because you have, I'm going to do it here again, 1 plus x squared to the 1/2 times x. So let's copy let's integrate the first one, differentiate the first one, so it's going to be half 1 plus x squared to the minus half. Okay, differentiated the first one, copy the second one, plus the differentiation of the second one times the first one. Hold on just a second. Oh, no, I'm going crazy here, guys. This is already the second one. So let's do this. You have 1 plus x squared to the 1/2. And you want to differentiate this, so 1 plus x squared, half times 1 plus x squared to the minus 1/2 times the differentiation of the inside function, which is 2x. You simplify this 2 with this 2, and you have x divided by the square root of 1 plus x squared. This is the first derivative, it's already here. Now, the second derivative, so you have, you can use either the product rule or the differentiation rule, or the division rule. I'm going to use the division rule. So it's remember, the derivative of f of x over g of x. I'm going to tell you what the formula is now. So it's going to be g of x, so it's 1 plus x squared to the half, all right, times the derivative of the first one, of the numerator, which is just 1, minus the numerator times the derivative of the denominator. The denominator is 1 plus x squared to the half, so it's going to be times, all right, minus x, and the derivative of the denominator, which is going to be half, and then you have 1 plus x squared to the minus 3/2. Okay, because it's, sorry guys, to the minus half. It's confusing, I'm going to recap this. So it's the first one, 1 plus x squared to the half times the derivative of the numerator, which is this one here, the x, minus the numerator times the derivative of the denominator. The derivative of the denominator is going to be half 1 plus x squared to the minus half, okay, times the derivative of the inside function, which is 2x. The whole thing divided by the numerator squared, so 1 plus x squared. Okay, that's the thing. Now this x, I'm just going to put it over here because it's multiplying, I'm getting out of here. This 2 I'm going to simplify with this 2 here, okay? So this is what we're left with. Now get this. You have this thing here, okay? One thing that we can do, because this is the final answer, but sometimes the book likes to simplify this. So let's try this. I'm going to separate the fractions, okay? Got a minus here, so I'm going to separate. So you have half minus 1. It's going to be minus 1/2. And here you have a minus x squared, okay? Now you have minus, okay, it's multiplying, right? You got 1 plus x squared here, 1 plus x squared here. Okay, so let's just copy 1 plus x squared. Now you have minus 1/2 minus 1, because this is a 1, right guys? I'm not talking about this 2 here, I'm talking about the one that's in here. So minus half minus 1 is minus 1.5. Yeah, minus half minus 1 is minus 1.5, which is minus 3/2. Okay, now one thing that you can do is to simplify this, so let's do that. Okay, because I already divided, yeah, Now here's what I'm gonna do. This is 1 divided by 1 plus x squared to the half minus x squared divided by 1 plus x squared to the 3 halves. And from here, from this point here, we're gonna go in there, okay? I'm checking the minimum common denominator, which is, here you got 1 plus x squared to the half, and here's to the 3 halves. So to the 3 halves is larger, so you pick that one. So it's gonna be 1.5 minus 1 minus half. It's gonna be 1, okay? So you put this one here, 1 plus x squared to the 1. That's what this is doing here. And then you have a minus here, you got a minus here. Fine. You have the x squared, so just put the x squared in there. And then you have 1 plus x squared to the 3 halves divided by 1 plus x squared to the 3 halves. It's just going to be 1. So you put a 1 in here, okay? And now what are you left with? You're left with 1 plus x squared minus x squared. You can just simplify this whole thing and cut this in here, okay? What are you left with? 1 divided by, 1 plus x squared to the 3 halves. This is the second derivative. I'm going to write that in here. Okay, just like that. 1 plus x squared to the minus 3 halves. That's the second derivative. Okay. I'm going to erase everything except the final formula there. All right. Now, you need from this formula here, you gotta know the largest value from 0 to 1. Okay, so you want the denominator, x is just in the denominator, and you want it to be small. So since it's squared, anything positive or negative that you put in here is just gonna make it larger. Okay, and if you put a 0, it's gonna be smaller. Because what is smaller? 1 plus 0 squared or 1 plus 1 squared? This one's going to be 1, this one's going to be 2. All right? To the 3 halves, so it's like elevating this to 1.5 and elevating this to 1.5. All right? You want this one. This is going to be the smallest one. Since this is the smallest value for the denominator, okay, you're going to have 1 divided by 1 in here because I'm going to plug the 0 in here. It's going to be 0 squared plus 1, that's 1. 1 to the 3 1/2 is 1. So in the end, it's going to be 1 divided by 1, which is 1. Okay, so 1 is the maximum second derivative. It's the maximum absolute value of the second derivative in the domain from 0 to 1. Okay, so this k, we're going to replace it by 1 very soon. What is b minus a? Is 1 minus 0. Is this 1 minus this 0? So it's going to be 1 cubed times 1 divided by 12n squared, which is just 1 divided by 12n squared. Well, so this is the formula of the maximum value, okay? The maximum error. The absolute error, yeah, this is going to be always positive anyway because of the n squared, so it doesn't matter. Okay, so this is going to be the largest error, and I want the largest error to be less than or equal to 0.01. So you want this to be less than or equal to 1 divided by 100. Now, what you can do is to take the reciprocal of these two and say that 12n squared is going to be greater or equal to 100. N has to be greater or equal to, well, it's going to be the square root of 100, which is 10, divided by the square root of 12. Okay. Now, when you do this in here, the book says that this is approximately 2.89. Right? Now you want n to be an integer. N is going to be 1 interval or 2 intervals or 3 or 4 or 5. How many intervals are you going to have? Since n has to be greater than or equal to 2.89, you know that if you put an n equal to 3, okay, you use the trapezoid rule with an n equal to 3, and when you apply to this formula here, you're going to get an error of less than 0.01. So let me try to develop this. Okay, so we found out that we got to use n has to be equal to 3. Let me do one thing here. Well, let's use the trapezoid rule. Okay, so what is the trapezoid rule? The integral from 0 to 1 of square root of 1 plus x squared dx is going to be an approximation of the trapezoid rule, which is b minus a divided by 2n. So b minus a is 1 minus 0 divided by 2n. 2 times 3 is 6. So you have 1 6, right? And then you're going to use this formula. You're going to use this formula with, oh yeah, there's something else too. What is the size of the interval? It's b minus n, a divided by n, which is 1 minus 0 divided by 3, which is 1/3. Okay, so you want the square root of 1 plus 0 squared, right? Plus 2, because remember, in the trapezoid rule, the first coefficient is 1, all the others are 2 except the last one, which is also 1. So 2, the square root of 1 plus 1/3 squared, which is going to be 1/9, plus 2, the square root of 1 plus 2/3 squared, which is going to be 4/9, plus the square root, and this is the last one because n is equal to 3, so that means you have 4 terms, 1, 2, 3, and 4, right? So the fourth term is the last one, its coefficient here is 1, so it's going to be 1 plus, it'll be 1, right? 1 cubed. All this, you're going to add it all up, and it's going to go up to 1, you're going to multiply to 1 divided by 6, which is it's also an approximation of 1.154, okay? So, since you know that this is within this error margin here, you can say that the result is actually 1.54 minus 0.01 and 1.154 plus 0.01. So the range is 1.144 all the way to 1.164. You know that the result of this is going to be within this thing, okay? I mean, we found an approximation 1.154, okay? And there's a margin of error because it's the trapezoid rule, it's an approximation. So you can be sure it's guaranteed it's within this margin here. It goes from 1.144 to 1.164, okay? Because we used the N3 and we found out through all this process that using an N3, you're going to have an absolute error of 0.01 for going over or under, okay? So that's it. Guys, if it's not clear, how did I find these numbers here? Okay, I just said that 1.154 plus 0.01, and this is going to be minus 0.01. Okay, so 1.154 plus 0.01, you got this. 1.154 minus 0.01, you get this. So it goes from here all the way to here. And that's one of the uses for this the error limit of the error boundary for the trapezoid rule, and for Simpson's rule is going to be the same thing, right? Now the proofs where these formulas come, where these formulas come from, I'm going to show in the following videos, but it's going to be in another playlist because it's complicated. Just as a recap, the absolute error for the trapezoid rule is going to be less than b minus a cubed times k. Well, I'm just going to write it times the maximum absolute value of the second derivative of f of x within the domain, okay, divided by 12n squared. And for the Simpson's rule, the absolute value of the, and all of this has to go into the absolute value. Why? Because b minus a cubed, well, b is always going to be positive, larger than a, so cubing it, it's fine. All this is going to be positive. Okay, so the maximum error for the Simpson's rule, the absolute value, right? It's going to be less than b minus a to the fifth. I'm going to put it down here. B minus a to the fifth times the maximum absolute value, the maximum absolute value of the fourth derivative of x within that domain, okay? All of this divided by 180 n to the fourth. These are the formulas.